Good day, and you're most welcome to today's session of the CNPS. This is one of our fortnightly presentations where we deal in some depth with regard to some ideas in modern analysis of theoretical physics. Unfortunately, the speaker is not here yet. I was expecting him to be here 10 minutes ago, but I have a few announcements. Before coming to announce the details of today's presentation, and indeed to introduce the speaker, I have an announcement to make with regard to our annual fundraiser. Now, the CNPS is very happy to have the dedicated support of all our members, who pay a small membership due. But unfortunately, that doesn't cover all the costs. There are significant costs involved in hosting the sessions and paying for the server and administrative essentials. So we normally have an annual. Yes, the speaker just said that he's here. That's fine. We normally have an annual fundraiser, and that has been launched. So what I'm going to do, without further ado, is I'm going to show a very, very brief video where David de Hilster is just going to tell you all about that and how to give a small amount of money. Because actually, it is a bit critical. It's suggested that if there isn't this ancillary funding available before the end of this year, our system could collapse. So it's quite essential. So let me put on David now.
Hello, my name is David de Hilster, and I'm president of the John Chappell Natural Philosophy Society. Our organization is unique in the world in that we allow for serious criticisms of mainstream science, from physics to cosmology and from math to philosophy. And today, this organization resides 100% online. If you enjoy our Saturday morning talks, our websites, and the community of amazing critical thinkers you can interact with on the internet, then please consider contributing to our annual fund drive. It costs almost $3,000 per year to keep our internet presence and our Saturday morning talks alive and well. I want to thank all of our members who pay monthly and annual memberships, which is vital to our day-to-day operations. But unfortunately, this is not enough, and that's why we're looking to raise $2,000 in our 2024 drive. So if you don't want this organization to disappear, and you think that its mission is important, then please consider donating to the CNPS. It's vital to keeping science moving forward. Please go to fund.naturalphilosophy.org and donate today. Thanks once again from all of us at the CNPS. Your donation is vital.
Right. Well, thank you very much for your attention in that regard. Now, so today's subject, we're proposing to have a talk by Dr. Stephan Gift, who actually is at the moment trying to log into the green room, because at present he's only in the social media entry system, which means that he doesn't have a possibility of speaking. I think he's gone into last week's session, because the problem with the link actually is that if your browser hasn't been sort of cleared out, it automatically goes to last week's session. So it remembers that generic mail. Or address, really. However, Stephan is from the University of West Indies in St. Augustine, Trinidad and Tobago. And today he's speaking about a modern approach to space-time physics. He basically says that the presentations will compare the Lorentz Transformations with Selleri Transformations using 12 different tests. Well, actually, I think he's going to be looking at 5 different tests in details. I think he's investigated in his other papers 12 test, but he'll be looking at 5 tests in detail today. Okay. So he says, we show that the Lorentz transformations of special relativity, despite their almost universal acceptance, fail 5 straightforward tests. The first 3 of these tests are based on the very successful GPS, which we believe provides incontrovertible experimental evidence and is a game changer. The remaining 2 tests are the well-known Michelson-Gale experiment, which is rarely, if ever, found in the SR texts. He asks why. And the lesser-known Wang experiment, which after 20 years remains unexplained by SR. We also show that transformations involving a preferred frame developed by Franco Selleri and published in the mainstream literature are successful with these and other tests with no paradoxes. We therefore advance the Selleri transformations as the space-time transformations that best accord with the physical world. Now, so just to get back to how do I get into the green room? So our speaker's asking me how to get in, so I better say, go to HTTP.
Yeah, I've put up the URL and I pasted that in the YouTube for Stephen to get in.
Is that today's URL rather than the generic one?
That's today's URL I've got up on the screen.
Okay, in the private chat, is it? No, in the comments.
Well,
I see. Very good. I have it here.
Screen.
Okay.
And in
okay, I'll just answer him because he's if he doesn't see it. Well, I'll type it out again just to be quite sure. HTTPS StreamYard.
Yeah, the other thing, the problem is that when you go to the generic link that is on the email, which is, live.naturalphilosophy.org,
yes,
there's something that needs to be done to update that link to the latest video, and sometimes that doesn't work. But for those who do try in the future, you can also get past that, I believe, by clearing your browser cookies, which is kind of inconvenient, I know, and then it will go to the latest version. Okay, we've got Stephen now.
Yeah,
okay.
He's in now. Okay. I'm going to add you, Stephan. You're very welcome. Thanks for bearing with us, because a number of people are having this problem that the generic link will send you to the previous one. Yes. So anyway, at least I typed in the correct one from Franklin's. Sure. Retrieving it. So you've probably missed the introduction. We had a quick introduction.
I actually heard it, Ian.
You heard it all?
Yes.
Okay.
Yes.
So that's fine. There's nothing more to do.
Yes.
Now, you told me that I just hand over to you. You're going to make your own introduction. Yes. And then whenever you want to show slides or videos or whatever, you tell me.
Well, my whole presentation is PowerPoint based. I have a PowerPoint presentation. So from start to finish, I had a set of slides to show.
Okay. So there are 2 ways of doing that. One way is for you to share your screen. Do you see at the bottom of the screen, there should be a banner, the central element to which says present?
Yes. Uh-huh.
Okay. Well, if you click that, it'll say present what? And if you have the slides, for example, on your desktop, you should be able to click on that and have control.
All right, just 1 minute. Let me try and
okay, you could try it if you wish.
Yeah. So you say click on, sorry, could you repeat that, Ian?
So click on present, Stephan.
Right. Uh-huh.
And then it says, well, you can either share your screen or you can click on slides. Maybe if you click on slides, provided you have the slides saved somewhere on your computer.
Yes, I actually have them open at the moment.
Oh, you have them open. Well, then it might be easier to share your screen, actually. So when you say present, just click on share screen.
Okay.
And then you have to click once more. It will sort of say, do you want to, what tab do you want to bring up? So
I'm seeing here, choose what to share with StreamYard.com.
yeah, I think you should really maybe take your entire screen and just click on
Entire screen.
Probably, yes. And then if you click on that, I'll cancel because I don't want to do it myself. So and just click on it then. Sharing
Okay.
screen was cancelled. No, that's my own. So we don't see your screen yet.
Well, no, because I have on my screen, I'm looking at you at the moment.
Are you looking at me and you? Because I have both of us.
Yes,
up.
yes,
Okay.
yes.
So you see not my screen; it's the general thing we're broadcasting. But we want you to overwrite that so that you're able to broadcast.
Mm-hmm.
Now we can try once more, but if this doesn't work, there is another way, and that is for you to send the slides to me, and then I can do it. But maybe they're a bit large to send into an email. So let me see. If you present, maybe. Let me see.
I mean, it's okay, Stephen, if you see everything from your screen, including Ian and this presentation. You can just go ahead and make your slides full screen, and then we'll get it.
All right. So this window that I'm seeing here, where it says choose what to share with StreamYard.com. What should I do? Cancel it?
Now, the easiest thing to do is to just select on the right-hand side, share entire screen. If you click on the top, click on entire screen.
Okay, yes.
Click on share on the right-hand side, then it will begin sharing.
Share on the right-hand side. I don't see share on the right-hand side.
It's on the lower bottom. You go to the upper right, you say click on entire screen, and then on the lower right, there's a button called share, and you click on that.
No, but you have to do one more thing before you get that because it's in gray. So when you see at the top left your screen, just click on that again, and that should enable the button on the bottom right that Franklin is referring to.
All right, Ian, could we go over it again? Because there's something on my screen that I don't think you all are aware of, which is asking me for information. You see, it says, this is apart from, all right, let me cancel that. I think we should go again. So yeah, I'm going to click on present. I'm clicking on share screen. Then it has share screen sharing tips. I click on share screen again. And then this little window comes up.
And what does
the little window, is that at the top left?
No, it's right in the middle of my screen, or to the upper portion of the middle of the screen.
So let's just go through it again. When you click present and then you click share screen, it says choose what to share. You then click on the right-hand top entire screen.
Okay.
Okay.
Yes,
now,
I've done that. Yes.
If you go down just a few millimeters on the left, you'll actually see the screen. It says entire screen.
Well, I've clicked on entire screen. Yes.
Yeah, but you have to click on that. It's twice. You have to do it twice. You have to click on that actual screen. Just put your cursor over.
Mouse below onto where you see your screen and click on that.
I'm sorry, could you repeat, Franklin?
Beneath the entire screen, you should see a rendering of your actual computer screen. Click on that.
Okay.
And then when you do that, then the share.
No, I'm nothing is happening.
We're getting some comments that this should have been done beforehand, which I agree. I apologize for this.
Yes,
we also have a snide comment that these are the guys who are overthrowing physics and we can't even get this thing up. Point taken. I apologize.
It should say like screen 1 or something. I mean, I have 2 screens here, so I can't do exactly what you're saying. But then the share button should become ungray and you should be able to click on it.
Now, wait a minute. Something's come up.
Okay, we've got your screen. Yes, we see
Yeah,
your.
that's because I got it here and I put it up.
We've got
So
the.
can you put your slides up now on your screen? Yes. Okay, I'll. That's it. Perfect. And we'd ask people to maximize their screens by clicking on the bottom right icon.
So Ian, are you all seeing the screen now?
Perfectly.
Yes, you can also click on that little banner there.
This one here.
Well, not that one, not to stop sharing, the link that's beside it, which is to hide that thing there.
Sorry, I'm not with you. Hide what?
Oh, well, Stephen has to do it. There's a little hide there on.
Yes, the hide. What to do with it?
Yes, you click on that. There you go. Now we got your full screen. You may start your presentation.
You ready to go? Okay, great.
Okay, it's all yours.
Yeah. May I proceed, Ian?
Yes, please proceed.
Okay, right. So good morning, everyone. My name is Stephan Gift. I am a professor at the University of the West Indies, Professor Emeritus of Electrical Engineering. My university actually has over 50,000 students and it has 5 campuses, one of which is online, just to tell you a little bit about me. I have taught there for many years and conducted research in electrical engineering. I have published 1 book, Electronic Circuit Design and Application, co-authored with Professor Brent Mundy of the University of Calgary. And this book is in its 2nd edition and doing quite well. But I've also been conducting a fair bit of research on special relativity. And that is the basis of the talk for this morning. And I wish to thank the organization, and in particular, Ian Cowan, for allowing me the time to do this presentation and have this audience. This is a summary of my presentation. We show that the Lorentz transformations of special relativity, despite their universal acceptance, fail 5 straightforward tests. Now, the notice said 12, and I had, in my initial correspondence with Ian, I had set 12, but I determined that really it is better to reduce the number so that I could do a reasonable presentation in the time that I have. So I had corrected it subsequently, but he didn't pick up the correction. So you saw 12 and 5 coming through. It's really, I'm going to discuss 5 tests this morning. And incidentally, I sent a copy of the paper is available at ResearchGate. The paper has a fuller discussion of what I will be presenting today. The first 3 of the tests are based on the very successful GPS, which provides incontrovertible evidence, in my view, against the Lorentz transformation, and I consider the GPS to be a game changer. The remaining 2 tests are the well-known Michelson-Gale experiment and the lesser-known Wang experiment. We also show that transformations involving a preferred frame developed by Franco Selleri and published in the mainstream physics literature are successful with these and other tests. All the 5 tests, the Selleri transformation passed them and produce no paradoxes, and this is key. I am therefore advancing that the Selleri transformations are the correct transformations and best accord with the physical world. Now, the central problem of relativity, and we need to define the problem very carefully, because I see in all the various discussions that different considerations and are taken up, things get confused and so on. I want to make very clear what is the problem that I have certainly focused on, which is find the transformations connecting 2 inertial frames, an S, an initial frame which we shall designate S, in which the light speed is c, and I will come back to that later, and another inertial frame S prime. And of course, we set them up in the usual way with S prime moving along. They're coincident at initial conditions, and the S prime axis moving along, or the X prime frame rather, moving along the X axis, and they're coincident. And as I show in the diagram, that's the normal way we set it up. Those transformations which we are looking for then, which is referred to as the central problem of relativity, these transformations, these new transformations must reduce to the Galilean transformations when the velocity at which S prime is moving away from S relative to S is very much less than the speed of light. And I have indicated there on the screen the Galilean transformations with which we are all familiar, so that the new transformations must reduce to these the Galilean transformations as a requirement. Now, in solving this problem, and of course it wasn't exactly set up that way in times past, but I am setting it up now in this way to make clear what it is we are trying to do, and if and indeed we are achieve that objective. So Einstein used two postulates: the principle of relativity, which says that the laws of physics are the same in all inertial frames, and the principle of light speed constancy, which says the speed of light in a vacuum is the same in all inertial frames. And from those two postulates, he came up with the Lorentz transformation, which are listed there below. I don't need to go through them. We all know them with the usual gamma factor. Now, because of the principle of light speed constancy, all of inertial frames under the Einstein paradigm have constant light speed. So it means there's no preferred frame. Even though I designated frame S as having light speed c, it turns out in Einstein's case, all of the frames, all S prime frames also have light speed c, so that there is no preferred frame in this representation of the problem, or this solution of the problem. Selleri used two experimental facts, and I should go back. Those two postulates at the time, well, they actually, if you go through Zhang's book on the experiment, special relativity and its experimental foundations, you will see neither of these two postulates has been confirmed, even though many physics books claim that the light speed constancy postulate has been confirmed. That simply is not true. But let us move on. Selleri used two experimental facts: two-way light speed constancy, which has been experimentally confirmed, and dilated muon decay time. That too, where the lifetime of a muon during decay is dilated or reduced. The lifetime is extended as the particle goes at a high speed. So those two facts, he used them, and he came up with this set of transformations here. Now, the space transformation is just the same as the Lorentz transformation, but the difference between the two sets of transformations is in the time transformation. The Selleri time transformation is this simple equation here, and if I go back, you will see that the Lorentz transformation has a space-dependent component in it, which is very critical, because that makes a profound difference between the two. So now, what are we trying to do? Well, actually, I'm saying in this slide that the Lorentz transformations correctly predict several phenomena. And I recall last week that one attendee was questioning what has special relativity done? What has it achieved? Well, it has achieved quite a lot. All of these phenomena here, transverse Doppler, that's not available in classical physics. It is new, predicted by the Lorentz transformation and confirmed to be true. Relativist, and we know what transverse Doppler is. But relativistic beaming, perhaps lesser known, where if you are in moving with a beam, let's say a torchlight with a beam shining ahead, and the person with that torchlight is moving quickly, then somebody on the ground looking at the beam will see the cone of the beam get smaller. The angle of propagation of the beam will get smaller. And this has been verified in those collider experiments and so on. So relativistic beaming has been observed. Compton scattering, where a photon strikes a particle and how it scatters. That has been confirmed. Relativistic elastic collisions, where you have one particle hitting another particle and they move apart. How that occurs, the angle of departure is actually quite different from the non-relativistic case. That has been confirmed. And this interesting phenomenon of Thomas precession, that was not predicted by the Lorentz transformation, but it was explained. It was observed way back in the 1920s that a certain kind of splitting of what you call it, as they measure radiation given off from atoms, they're able to measure what the extent of the precession taking place. And they expected a greater precession of the electron as it goes around the atom than was actually observed. And Lorentz transformations actually explained that apart from the existing precession, which is something called Lama precession that occurs as a result of an induced magnetic field created by the movement of the electron as it traverses as it goes around the atom and crosses the electric field of the nucleus. A magnetic field is created which interacts with the spin, the intrinsic magnetic field of the electron and causes it to precession. That's called Lama precession. But Thomas precession is a phenomenon where, and I show this second slide, because they consider it a kinematic effect that I myself haven't really understood the forces involved, but it is pointed in the diagram that you see, the Lama precession, the vector is pointing upwards. I don't have it illustrated on the diagram, but what I show is the Thomas precession, which is the vector pointing down, and that reduces the Lama precession to half its value. So this was a phenomenon that was explained by the Lorentz transformation, and it is now considered, I've seen it in at least one textbook, that is taken as confirmation of the correctness of the Lorentz transformations. Well, as it turns out, I have been able to derive the Thomas precession using the Selleri transformations. It's not been done before. I think my derivation was the first one, so that no longer can the relativists claim that Thomas precession is only explainable by the Lorentz transformations. Okay. So moving along, we have 5 tests this morning. As I said, not 12. We're going to do 5 tests of the Lorentz transformations and the Selleri transformations. Now, I just showed you 5, listed them, that the Lorentz transformation tested correctly. And so did too the Selleri transformations. The tests that I'm discussing this morning, these 5 tests, I would tell you at the outset that the Lorentz transformation has failed all 5 of them, while the Selleri transformations have passed all of these tests. So I want to go through them carefully, and I certainly would welcome all the comments that we have, because I told you that I consider the GPS to be a game changer. And those first 3 tests that I have listed there are all based on the GPS system and its operation. So let's go into it right away. The first one, let us try to determine the speed of light between 2 fixed points on the surface of the Earth, 2 points A and B east of A. And we're going to find the light speed with light traveling from A to B, I call it CAB. And light speed going from B to A, I call it CBA. So that is what we have set up. Let us now see how the 2 transformations, what predictions they make for those speeds. The Lorentz transformations, and what you have here is I have taken the differential of the 2 transformations in order to find the speed predicted by these transformations. It's a simple derivation. So I take dx prime, I find dt prime, and I divide the two of them. Remember, the prime is in the moving frame, the S prime frame. And when you go through the simple analysis, we get that the Lorentz transformation predict constant light speed c, which of course is not surprising because these transformations were derived on the basis of a constant light speed as one of the postulates. So it's certainly consistent. It is predicting constant light speed. So it says the speed between A and B to A is the same. On the other hand, the Selleri transformations, when you do the same thing, take a differential and you divide and you get gamma squared into C minus V. So for light speed from A to B, for V very much less than C, this goes to 1 and you get C minus V. And for light speed from B to A, you just change the V to minus V in there and you will get C plus V. So these are clear differences in predictions. Good, there's no commonality there whatsoever. One set of transformations predict constant light speed. The other one predicts variable light speeds. Let us now use the GPS in a way that I have not seen it done before, except perhaps by Selleri. And no, there are a couple others. Mami and Kelly actually did come up with these results by measurement using the GPS. But let us go to an analytical procedure to get these light speeds. So we want to find the one-way speed of light going east. The light travel time between fixed points using the GPS clocks are given by this equation here. Delta T prime is equal to the integral of d sigma prime over c plus 2 omega e over c squared integral of d z. Now, d sigma prime is the short length traveled. Omega e is the angular velocity of the Earth. And this is a vector that is, and I will show you what this daz is in a little while. Just let's accept the equation. And in fact, I put my reference here. And all to do with the GPS are coming from Ashby's paper, which I do commend to you all. So he has this is equation in there. And what this represents is you can find the time between those 2 points. In fact, this equation is what represents the time shown by the synchronized clocks of the GPS. They are captured in this equation here. So this has been experimentally confirmed. And therefore, it is as if you are using the two clocks to actually measure the time. So when I go through the integration for light to travel east a distance L from A to B, I get this simple equation. Here's a straightforward analysis. And therefore, I have the time. I know the distance is L. The time is L over C plus LV over C squared. So the speed from A to B is L divided by the GPS clock time, and I get C minus V, which is what I got with the Selleri transformation, and is contrary to the speed rather you get with the Lorentz transformation. If you do the same thing for light traveling west, you take the same equation, which represents what the clocks will actually measure. Remember, they are synchronized clocks. And by the way, they're able to synchronize them because of the existence of the Earth-centered inertial frame, the ECI frame, where it is known that the light speed is constant in that frame. And that is what allowed them to synchronize these clocks. And the time we get now, delta T BA, going the other way, is L over C minus LV over C squared, which is a shorter time. And when you work out the velocity, you get C plus V. So here's what we have, ladies and gentlemen. The one-way speed of light given by the GPS clocks is C minus V and C plus V. The Lorentz transformation says it's C, which is a fail. The Selleri transformations accord with what the clocks indicate, C minus V and C plus V. So clearly you see that the Lorentz transformations fail this test. And I would also add, this is the reason why clocks on the surface of the Earth cannot be synchronized using the so-called Einstein synchronization, where you assume constant light speed. If you use constant light speed, the clocks will not get synchronized. You have what they call, they introduce something called a correction. They call it a Sagnac correction. Well, it's a correction because the answer they're getting, the result they're getting is wrong. So they have to correct it. And I will come to that when we talk about clock synchronization as one of the tests. So let us move on. The second test is the time transformations, which I pointed out was quite different for the two sets of transformations. Good? The time transformation using the GPS, as it turns out, we are able to deduce what it is from, in other words, what time transformation guides the behavior of the GPS clocks. Good? So that equation here, clocks moving relative to the ECI frame run slow according to this equation here. The integral of dt prime equal integral of 1 minus v squared over 2c squared dt. You will find this in Ashby's paper. In the equation where he actually has this, in his paper, he also includes a term, a gravitational term. But once gravity is the same, which we are assuming here, clocks at the same gravitational potential, then this is what that equation reduces to. You will find that this equation in his paper, and again, it is the equation that governs the behavior of the clocks as they move in orbit around the Earth. Now, if I integrate this equation over the satellite path, assuming the v is approximately constant, I get this equation here. And this equation really is a good approximation of t prime equal to t over gamma when you expand it and reduce it for v very much less than c. In other words, for v very much less than c, the equation that governs the behavior of the GPS clocks as they orbit the Earth is this equation here, t prime equal to t over gamma. So that is it. I have it here. This is the equation. The Lorentz transformation equation, time transformation, is this, which can be written in this form. Good. This can be reduced or written as this. And you could see now when you compare this with this, you see there's this extra term here, which makes this equation different from this. But the Selleri transformations have the same time transformation as the equation is the same equation as the equation governing the behavior of the GPS clocks. So once again, the Lorentz transformations fail. This is an actual experimental test. I want, ladies and gentlemen, I want you to recognize what this means. That Ashby's paper has an equation for the behavior of the clocks, which they have confirmed experimentally. And it gives us the opportunity to compare that equation with the time transformation of the Lorentz transformations and as the Selleri transformation. And you can see that one fails, that is the Lorentz transformation, because they have this extra two. So that's test number 2. Let's move to test number 3, clock synchronization in GPS. This, of course, is hardly ever discussed in the books. But it is in Ashby's paper, which I referenced there again. He has this equation, dt prime equal to d sigma prime over c plus 2 omega e over c squared daz. And this little graph I drew here, this little diagram, sorry, this O represents the axis of the Earth is like up and down vertically through this point. And you can see O is a point on the surface of the Earth where the light is being projected along the arrow in the direction of the arrow. D sigma prime is the distance traveled here at an angle is supposed to be theta prime. The angle with respect to the horizontal, or if you like, a line of latitude. The DAZ is this area here that is mapped out by this vector as it moves. This is parallel to the equatorial plane. And it's defined in his paper, and you could go and take a look at it there. So this is what they use. Now, this is similar to the equation I used for the time to traverse a distance as measured by the clocks. Well, it is that same equation that is used to synchronize the clocks. And how they do it is they will send a pulse from one clock with the information of when it was sent. And when it gets to the other clock, you must know the second clock must be set to the time of the first clock plus the time that this equation gives you. And when you do that, the two clocks will be synchronized. Good? So that is the procedure. And if you go the other way, then you have to use a minus sign here instead of a plus sign. So with the GPS, this is the synchronization algorithm as I refer to it. Let us try to produce this algorithm using the Lorentz transformation. Now remember, C, the speed of light, which I call C prime, in the moving frame is C. And the moving frame here is the surface of the Earth, which is rotating. It's moving relative to the ECI frame. The time would be given by that distance I indicated to you, d sigma prime, over the speed of the light. Now, this just gives you the first term in this equation. It doesn't give you this term. And this is where Ashby and all supporters of relativity add this term and call it a correction. And in order to justify this correction, they have to turn to general relativity in order to get this, which is in fact what Ashby uses in this paper to get this term. But we're talking special relativity. And the Lorentz transformations cannot give you this equation. In fact, they give you a wrong result, and therefore they're wrong. It requires a correction, this term. The Selleri transformations, on the other hand, and I ask you to just observe closely, please. I didn't state this equation here before. This equation, but I'm introducing it now. This is Selleri transformations predict that the speed of light in the moving frame is given by this expression here, where theta prime is the angle of the light to the x-axis. If in fact you put theta prime equal to naught, you will get the result we derived earlier. But this is the more general expression, and of course I couldn't, I'm introducing it here, I can't derive it here. It's a little more involved to derive this result. But you will find this in Selleri's papers, and I have actually independently derived it myself. So if we now, to find the time, we divide d sigma prime by c prime, and we do that here, where c prime is this. And when you go through the analysis, you actually get the synchronization algorithm given in Ashby's paper. This, you cannot get it with the Lorentz transformations. That is established. You have to go to general relativity to get it. But we're talking about the Lorentz transformations which fail. And the Selleri transformations require this approach requires no correction. You see the result right here. So that's test number 3. Test number 4, the Michelson-Gale experiment. That's the one I had in my introduction as to why the textbooks do not have this experiment. I have never seen it, but I don't want to say it's never there. I may just not have seen it, but it's certainly true to say it's rarely, if ever, discussed in the special relativity textbooks. Now, here we have a light source sending light in 2 directions around this. One going from A, B, C, D, A, and the other one going from A, D, C, B, A, and then they are combined in this interferometer. This other smaller part here is to establish a reference for comparing the result of this one to know how much phase or fringe shift was introduced by the larger rectangle. These long arms lie along lines of latitude, and the shorter arms lie along lines of longitude. And of course, when you do the analysis, you find that the fringe shift, delta t prime, is the time difference between the two counter-propagating beams. And when you multiply by c and divide by lambda, the wavelength of the light involved, you get this expression here for the fringe shift, where omega is the angular velocity of the Earth, a is the area of the rectangle, and phi is the angle of latitude, the latitude at which the experiment is conducted, and lambda is the wavelength of the light. Good. So that experiment has been experimentally confirmed by Michelson and Gale back in 25, and it has been subsequently reconfirmed several times since, and we know that this experiment has been repeated several times. Now, what does the Michelson-Gale, the Lorentz, what do the Lorentz transformations say? Well, remember the Lorentz transformations predict constant light speed, and they do so in all the arms of the experiment. So therefore, and I go back a bit, since according to the Lorentz transformations, light speed around this way is the same as light speed around this way, which is c, constant, then the time difference will be 0, and there will be no fringe shift. The Selleri transformations, on the other hand, with this general expression for the light speed, when you put in theta prime equal to 0 and for in one direction, and theta prime equal to 180 degrees for the other direction, and 90 and 270, and you put in those numbers, you get, and you go through the analysis, which I have in my paper, the full analysis, you will find that you get this expression. I actually worked it out, and this is what the Selleri transformation give, which of course is the correct result for the fringe shift caused by counter-propagating light beams. Now you can understand why it's not in the textbooks. This experiment is not in the textbooks because they will get 0 phase shift, because remember the Michelson-Morley experiment is very similar to this in that you just remove this mirror C here, and you have a Michelson-Morley apparatus, and you have to just reorient these mirrors. So, and the Michelson-Morley experiment, everybody has considered that the light speed in the speed in the arms, the light speed is c. Well, just the same way it's c here, and we saw the prediction from the derivation that I gave. So that it's going to give 0 phase fringe shift, and therefore it's unexplainable by the Lorentz transformations, and hence the reason it is not in the textbooks. You will see the Sagnat experiments. That is a few textbooks have that, but I won't comment on that now. If anybody wishes to comment on that later, we could bring that up. But certainly you can see here that the Lorentz transformations failed the Michelson-Gale experiment. And I come to the last test, the Wang experiment. Now, this is an experiment performed by Wang and his associates back in about, I think it's 2003, where there is this, these long arms here are fiber optic elements that are spun around quickly. And this apparatus here, they call it the fiber optic gyroscope, to send, it's traveling with the arm, it's traveling with the medium, and it's sending light in 2 directions and detecting that light as it goes around in both directions. So the detection, the transmission and detection apparatus are in the same frame as the moving fiber optic elements. And experimentally, what they got was that the difference in time between the 2 counter-propagating beams is given by 2LV over c squared, where L is the length of the fiber optic element, V is the velocity that it's moving, and it's independent of the refractive index of this medium. So they change, if you have different, n to different values, it doesn't matter. The expression is independent of n, experimentally confirmed. Now let's see what the Lorentz transformations say. Remember, the Lorentz transformations say that light speed is c, and in the medium, it will be c over n. And what has been done is that researchers or the theorists have taken this c over n in the medium, and they have put it into the Lorentz transformations of the velocity formula. They call it the velocity composition formula under the Lorentz transformation to get the speed in the lab. I'll explain why we're doing this in a moment. So speed in the lab is equal to speed in the medium, which is c over n, plus the velocity of the medium over 1 plus vc over n over c squared. And when you work that out, you get this expression here, c over n plus 1 minus 1 over n squared all into v. This expression here was confirmed by Fizeau. This, by the way, 1 minus 1 over n squared is the so-called Fresnel drag coefficient. And this expression was confirmed by Fizeau in 1818, I think in the 1850-something experiment, that in fact this is true. And this is why Einstein said in one of his books, this was a very important experiment because it confirms the idea that here's what happens. You actually use his transformations to work out what this is. And he didn't have to introduce any coefficient. It came up naturally by putting c over n in the medium into this formula and getting c in the laboratory. And here we had this. So he was very happy with this. And one of the books described this as a beautiful application of the Lorentz transformations. When you find the difference in the propagation times in the medium, though, remember the speed in the medium is c over n. So that is L over C over N minus L over C over N, and you get 0 because the light speed in the medium is constant. So you can't get a time difference and you will get 0 fringe shift. Now let us turn to, before I go to what Selleri says. The Wang experiment, actually, there was an attempt by these authors, Ori and Avron. The paper generalized Sagnac Wang Fizeau formula in a top mainstream journal, Physical Review, back in 2016. These authors, they acknowledge that the light speed is c over n in the moving frame, in which case, of course, they can't get a difference in light counter propagating in beams having different propagation times. So what they do is they Lorentz transform the times using the Lorentz time transformation from the moving frame to the laboratory frame. Then they find the time difference in the laboratory frame. Now they get the right answer, but they are in the wrong frame. This must be done in the moving frame, not in the laboratory frame. This paper, I mean, I could not believe that this paper would have gotten published in this top journal, because they're giving the answer, but they got the right answer, and I guess that's why they published it, but it is in the wrong frame. The frame in which they measured the characteristic of the difference in propagation times is in the moving frame. So this presentation, gentlemen, is completely wrong. Now let us turn to the Wang experiment with the Selleri transformation. I accept, and I worked this out myself, I accept that the laboratory light speed is given by the Fizeau expression. That has been experimentally confirmed. I take those and I stick them into the the Selleri transformation of velocity from one frame to the next. The same corresponding, it's like the velocity composition formula using the Selleri transformations. So I get that the speed of light in the medium is given by gamma squared into C in the lab and minus and plus V according to which direction, if it's moving, if it's in the same direction as the light is traveling in the same direction as the movement of the medium, it's the minus sign. If it's in the opposite direction, it's in the plus sign. And this is the expression that you get. And when you stick that in, so this is the speed of the light in the moving frame as predicted by the Selleri transformation. When you put that in, work out the time difference for counter-propagating beams in the moving frame, you get the answer that they found in the actual experiment. This is another experiment you will not find in the textbooks because there is no proper explanation for it. That explanation I just showed you is invalid because they are finding it out in the wrong frame. So the Selleri, so far, here's what we have. The Lorentz transformations fail because they give 0 time difference. The Selleri transformation pass, they give you the correct answer. So, summing up, everyone, we have 5 failed tests of the Lorentz transformations. One-way speed of light, the prediction is c. The value is c plus or minus v in the east to west direction. And by the way, we can get a general expression for light in any direction using the Selleri transformation, but we won't go into that this morning. This east-west light speed will do to show that the Lorentz transformations are incorrect. We show that the time transformation of the Lorentz transformation is wrong, as established again by the GPS clocks. They adhere to or are governed by a time equation, which is different from the Lorentz time transformation. The GPS clock synchronization, you can't get the algorithm using the Lorentz transformation. You can with the Selleri transformation. And then these 2 experiments, the Michelson-Gale experiment and the Wang experiment, clearly you can see that the Lorentz transformation failed. So these are 5 basically confirmed results from confirmed by experiment where the Lorentz transformations fail. So this is not a question of, I remember last week about the discussion with that has always gone on, that has gone on for so many years about the twin paradox and all of that, and all kinds of explanations and stuff coming up to try to explain it away. These tests are very clear. There is no, I don't think there's any room for interpretation or reinterpretation. They are absolutely clear and simple. They're very straightforward. So I would love to hear the supporters of relativity counter these 5 tests. And by the way, there are several more, but I've selected these 5 for discussion this morning. And as we approach the hour, the STs pass all the tests that we have done. The first 5 that I indicated that they passed, and the first 5, sorry, and the second 5. And these are the equations for the Selleri transformation here. But the Lorentz transformation, because of this time, this invalid time transformation, it fails 5 tests. And of course, it only needs to fail 1. Only 1 test need be failed. It could pass 1,000. If it fails 1, it has to be rejected, as we all know. So I thank you, colleagues, and I'm open for questions and comments. Thank you very much.
Well, thank you very much, Stephan. That was quite fascinating. And I think I have a slight advantage on many of our participants in that I've read your paper. So I was rather familiar with what you were saying, but you've expressed it very cogently, and thank you very much for doing that. I think there's going to be a lot of discussion. There are questions coming down. We have an hour to do that. Yes. Perhaps just before scanning through the questions quickly and then giving the floor, because I know people like Nick want to come in and deal in some detail with some of these aspects, which we would encourage. I think Harry's been trying to get in, but he's not able at present. But maybe just 1 or 2 observations, if I may. You know, I sort of see that these tests, which fundamentally indicate what you advocate, indeed, are sort of based on the Sagnac effect, which you did refer to, and the lack of taking into account of that in the Lorentz transforms. And the problem with the Lorentz transforms is that the speed of sound, as you've indicated, is rendered.
Yeah. Go ahead. Sorry.
The speed of sound in the LTs is not only independent of the speed of the source, but also the speed of the observer. Now, with regard to the Selleri transforms, the latter is not true. It obviously varies. But I'm wondering why the Galilean transforms might not be sufficient. Because they would also pass these tests, actually. And for example, you indicated that in the composition of speeds formula, you get this in the Selleri transforms, which for V very much less than C, it reverts to C plus or minus V, whereas in the Galilean transformations it's exactly C plus or minus V. So one way to distinguish the two, whether the Selleri transforms are an improvement on the Galilean transforms, I'm convinced that they are an improvement on the Lorentz transformations, but would be to do a high speed test analogous to some of these points that you raised, and you'd be able to show that whether the difference in speeds or the addition is C plus or minus V, or it's the exact expression which you give from the Selleri transforms. So I'm just wondering if you'd like to comment on one or two of those points before we hand it over to the more general discussion.
Absolutely, Ian. Are you still hearing me?
Yes, perfectly.
Beautiful. Okay. No, if you let me go back to. Are you still able to see my slides?
No, because it's my fault. I've taken them down. But I can
okay,
put them
that's
back.
okay. It's okay. It's all right.
Back now.
Okay. The test that failed. Sorry, the test that were passed. Excuse me. To comment on your belief that the Galilean transformation also passed these tests and may be adequate. No, the Galilean transformations are inadequate because those 5 tests that I have up there, which are the correct predictions of the LTs and the STs, the Galilean transformations cannot produce those, none of those 5. So transverse Doppler, relativistic beaming, Compton scattering, elastic collisions, Thomas precession are entirely, if I may use the term, relativistic phenomena that cannot be produced by the Galilean transformations. So I am clear that they are inadequate. They hold good down at very low speeds, which we have observed over time, which is why I had included and said the new transformations must reduce to the Galilean transformations when the speed, the movement is very much less than the speed of light. But beyond that, Ian, let me go back to the list. The Thomas precession, for instance, is impossible. None of those can you get with the Galilean transformation. So my comment is, you don't even need to go and do a high-speed test. We know they are inadequate because there are several results that they can't produce. Why I indicated in my test that the light speed, for instance, I think there's validity in what you're saying insofar as just to further demonstrate that the new result that I have put down, which is this one, for the Selleri transformations, where it is. Here we are. That is gamma squared into C minus V. Well, if you do go at a high enough speed, yes, it will move away from C minus V because gamma is in fact greater than 1, and it will actually go up. So I take your point there, Ian, that if you were to do such a test, it could further confirm the correctness of what I have up there.
Okay, and the one thing just before leaving this is that those other relativistic tests which you talk about, it would be interesting if you maybe consider, perhaps in the future, you might want to talk to us about that, because one might not be convinced about that. One aspect of what you've been doing today, yes, those. One aspect of what you've been doing today is the, instead of the time being invariant, it's there's a dilation factor, and it appears maybe that from what you're describing that you would advocate that the Selleri transforms are in accordance with time dilation.
Yes.
Whereas many of us might consider that there's actually no such thing as time dilation. It's merely that clocks, owing to some physical effect, have this property of the frequency changing with speed relative to the ECI. But I might leave it at that. I just thought I'd mention these few things, and in particular, your answer with regard to these 5 correct predictions.
Ian, on that point,
today, there might be interesting to have another talk about that.
Yeah, sure. I want to quickly just address that point you raised, because I don't want any confusion to be created whatsoever. When I talk about time dilation, it's just that I use that phrase because that's widely used, but we're really talking about clock retardation. I think Nick makes that point repeatedly, but I use them interchangeably. That is a phenomenon of a moving clock, good, and not actual time being dilated. So let us not create any issues there whatsoever. We're talking about...
It's only that in the Selleri transforms, you have T prime is equal to T over gamma, whereas in the Galilean, it's T prime equals T. So, it appears that there's some interpretation of a dilation there.
Yes, as I said, as time as represented, or how do we know what time is, Ian? We measure it with clocks. That's what we do. And what we have to take into account is that these clocks, when you move them quickly, they are affected by movement, just as they are affected by gravity. And that is what that equation captures.
Okay. Well, perhaps we may come back to that.
Sure.
But I'll just scan. There's been a lot of very interesting conversation here in the general chat.
I can't see it myself, but
no. Okay. Well, it's not. I prefer to deal more specifically with what you've talked about today, and I think we have time to bring a couple of the green people in the green room in, if they just don't mind holding on for a little further. I'm sorry, Harry doesn't seem to be able to get in, but Nick is there. However, people are talking. Franklin has been talking about this business of, light behaving in really the same way as sound does, and it's just the medium is maybe the ether in one case, and it's the gas or the air in the other case, and that's something I've studied as well, and I accord to. But there's some people disagreeing with that and getting confused about source speed versus observer speed and so on. But a number of people here, like question, for example, they haven't been familiar with the Selleri transforms, which is not surprising because they're not promulgated very well, and they're certainly not taught in undergraduate physics classes. So I think we could spend a lot of time going through those. But I think we might we might. Harry had one question here actually, which you may not be able to get to. He's talking about the Sanya correction. There's one point from Jim, maybe just before getting to others in the green room, Stephan.
Yes,
maybe
sure.
you'd like to comment on Jim Marston's. But he's asking you, could you comment perhaps generally on the Michelson-Morley type experiment? You have concentrated on the Michelson-Gale, which admittedly, as you yourself say, is not very well known.
Yeah. Sure, I can do that, Ian.
Could you say a few words on that?
Yes. The Michelson-Morley experiment is what is called a second-order experiment, in that the phenomenon to be detected or observed is proportional to V squared over C squared, where V is the movement of the apparatus. That is, in this case, it was the Earth. The problem with that is because it's second order, though the thing to be observed is very small. That's the first problem. And then the second problem with second order experiments is they are affected by other second order effects, like clock retardation, or I happen to be a believer in length contraction. So second order experiments are really unreliable. That is the problem with them, because the effect is so small. First order experiments are better. That is those where they are you are trying to detect a phenomenon that is proportional to V over C, where V is again the movement of the apparatus, or some movement, and that is much more observable. So, for example, the Michelson-Gale experiment is an example of a first order experiment, and that gave a clear indication. There are no ifs. You can't doubt what you observed. You can use the Doppler effect to produce a first order experiment to detect, for instance, movement through a preferred frame. In fact, the Doppler effect is routinely used to determine the speed of the orbital speed of the Earth. Routinely used, the Doppler effect. And then there's also the observation of stellar aberration, where you have, if I may call it, the Bradley effect. That's another first order result that which you can use to detect the movement of the Earth in its orbit around the sun. So that is the kind of experiment I believe we can use. Now, coming back to the Michelson-Gale, again, I say it's a second order. And really, we don't need to, now that we have GPS clocks, Ian and everyone, we have synchronized GPS clocks. So any time differences, we just use the clocks to measure it. And that is what we did here this morning with the equation that I use, which represents the time that would be measured by actual clocks captured in that algorithm. So there's really no need. I mean, Jim can go ahead and get it, doing the second order Michelson-Gale. By the way, I happen to think that experiment will yield a null result. I happen to think that. But I'm saying there's really no need, because we have first order results, including the results of the GPS clocks, to give us all the information that we need. And we don't need to resort, I don't think, to second order experiments, which are very difficult. The parameter being measured is very tiny because it's V squared over C squared, and therefore unreliable.
Okay, well, thanks very much. Just one comment here from Mohammed Hussein. He says, what are the 7 tests in which the STs pass and the LTs fail? But I think those are the other tests. You've dealt with 5 of the 12, and you indicated briefly, because he said to me, would you please answer my question? But I hope we've answered your question. If not, please come back, Mohammed.
Yeah. So he wants me to tell him what the other 7 are. Is that it, Ian?
Well, I think so. Those are the ones that you say are so-called relativistic tests.
No. The 5 ones that are passed, I don't count that in the 12.
Right. Oh, you don't?
Those are passed. All the 12, and I had reduced it to 5 this morning. The 12 are all tests failed by the Lorentz transformations. And that's the ones we want to focus on, not the ones they pass. We know they pass those, and that's great. But it's where you fail a test, then your transformations or your theory runs into problems when you fail a prediction. When you make a prediction and the prediction is unconfirmed or invalidated, then your theory fails. That's just how it is.
So there's another 12 tests which could be...
No, Ian, no. All right, let me just explain. Let me summarize it. I gave 5 tests where the Lorentz transformations passed. I wanted to establish that the transformations have done some good. So I gave 5 tests where it passed. But I have 12 other tests where it failed, and only 5 of which I gave this morning.
Oh, I see. Okay. So I'm a bit confused. I'm sorry about this, but others may be. So which tests did the Lorentz transformations ostensibly pass? I don't remember.
No, I showed them. Let me show you them. I said that. Here they are. Those 5. Transverse Doppler.
Oh, it's where they both, you're saying both LTs and STs pass with regard to those tests.
That is correct, yes.
Okay. Well, okay, so I'm confused as well, and I hope we've clarified that, Mohammed, somewhat. Thank you. You come back if not. Okay, well,
as you go through, Ian, I want to say the STs have passed all the tests to which I have subjected them, and I have gone through just about the full range of tests in the relativity text to test the STs. So they have passed all. If they fail one test, they too have to be ejected.
And I'm rather awkwardly suggesting that even though they seem to be, giving the results, one could distinguish between them and the Galilean tests by doing this high-speed sort of Sagnac type experiment, and maybe distinguishing whether the relative speed is v plus or minus c, or gamma squared into,
Yeah,
the more
yeah.
complicated expression.
Sure, I take your point there.
Yeah. Well, thank you very much. So
Mm-hmm.
let's see, is anybody I'll take down the slides for the moment. And if you want me to put them up again,
Yes.
I'll
Yeah.
do that.
You can take them down. It's okay. Yeah.
I've taken them down. Okay. So
Oh.
let's see if anybody in the green room, there's Nick there. So Nick has alerted me to the fact that he does want to go into some detail here. And we're very grateful to have him do that, because he's gone into this subject. I mean, he's a specialist in this subject. So Nick, it's all up to you what you'd like to address to Stephan or the rest of us. No, you're mute, Nick. You'll have to unmute yourself.
First of all, I'd like to congratulate Stephan on a really good presentation. And I think he does an excellent job in terms of comparing the STs with the special relativity version of the Lorentz Transformations. I'll just start by making 2 points about terminology, which could confuse people or have people go away with the wrong conclusion if they aren't really studying this in depth. As Stephan pointed out in the first point, I think in his chart, he is talking, when he's talking about the Lorentz transformations, he's talking about the special relativity version of the Lorentz transformations, and not Lorentz's original version of the Lorentz transformation. And I think in that comparison, I think he's made a lot of really good work, and it's done very well articulated. Now, I think Stephan would agree that the relativistic professors who oppose them are very intelligent. It's not because they're stupid that they have a different view. And then that they are, the problem is that they have become intellectually and identified with special relativity as being correct, either by writing books or papers about it, or taking their professor's word as they were taught as gospel. So it's possible that you, and of course I, can become so wedded to a particular view that we may overlook some obvious problems. Now, I would make the assertion that giving every possible benefit to the STs, that if one takes Lorentz's original version, every test that the STs pass, the Lorentz original Lorentz transformations would also pass. Now, I admit that Selleri went and did some new stuff, but what he did was a very natural extension of the Lorentz transformation to the variation on angle and things like that. The problem I have, therefore, or one of two problems, is that the STs don't really bring anything new. We should go back to the original Lorentz transformations, which basically Einstein plagiarized and converted into a relativistic version that really messed things up. In fact, the two transformations, the original Lorentz transformations and the special relativity Lorentz transformations, look identical mathematically, but because of the physical meaning of the velocity term, they are really at opposite ends of the physical physics spectrum of theories. So one must always, when one is doing this analysis, one must always be sure one is applying that math consistent with the context for the special relativity Lorentz transformations, if that's what the topic is, or consistent with the Lorentz's original version, preferred frame version, if that's the context which one is talking about. So that's one point. The other point is that I have problems with the STs is that their history really has a lot of relativistic trappings, because Selleri, who is a very good physicist, he won Italy's top prize for being a physicist, even though he was going against many of the establishment physicists. But I don't think he was well steeped in Lorentzian theory, and he started out with special relativity and began to evolve it step by step down into a full preferred frame. His first step, which he articulated in his book called Weak Relativity, which could really have been named Slightly Weak Relativity, was just to change special relativity's absolute simultaneity, relative simultaneity into absolute simultaneity. But he did this by arbitrarily selecting one frame as the frame that would define absolute special relativity, absolute simultaneity for all frames. And that left most of the problems of relativity. The other thing that I've talked about before is that you talked about one of the problems of the Lorentz transformation having the x term, the distance term, in the time transformation equation. That's the Selleri transformations have the same problem if it uses the same assumption about how clocks are synchronized. So basically the Lorentz transformations and the Selleri transformations will pass or fail the test because they're basically the same. If you use the same assumptions, if you apply them with the correct physics interpretation when you're doing those tests. That's the second main point. Let's make me one more terminology thing. You referred to the 5 phenomenon where the special relativity Lorentz transformations fail as relativistic phenomenon, but it's really more accurate to say that they're high velocity.
Sure.
Yeah. Okay.
That's fine. That's fine. Mm-hmm.
So let me add one thing. In that 1995 paper of Selleri's that you recommended to me as, consistent with your thinking, he has a very long section on the two-way constancy of the speed of light. And he's saying that this is foundational. But the problem is that the two-way speed of light is not constant between different frames. And, I can give you an example if you want. And the experimental evidence for it being constant is only at very, very low speeds.
So we could address Nick's points directly, or you might want to take a couple of points and just give us your response, Stephan. The other possibility is I'm having a few people wanting to come in now in the green room. I have Eric and Jim, and you could listen to them and maybe in the summary at the end deal with them. So would you like to say a few words on Nick's
Okay,
point,
yeah.
or shall I go to the other people?
Yeah, let me quickly respond to a couple of points.
Okay.
So the STs are not a natural extension of the Lorentz transformation, and it doesn't really matter. Nick and I, by the way, have argued these points before.
No, they are a natural extension of the Lorentz transformations.
All right, Ian, I am in disagreement with Nick as to his comments about the nature of the Selleri transformations. We have disagreed before, and we will continue to do so now. So we will agree to disagree.
Okay.
But I would certainly say that he said a couple of things. Just quickly, I believe remember what I said the central problem was to find the transformations that connect one inertial frame to another. And Selleri went through in that 1995 paper and papers subsequently, because there was evolution, but the basic transformations remain, and I am satisfied that they represent the real world as we understand them today. But I will comment on further Nick's points later on. Let's take some of the other comments.
Okay, just one comment, I think, which may be germane, just before we let Nick go at the moment, is Harry proposes that the preferred frame assumption is used by both Selleri and Lorentz. What would you say to that?
Yes, and in fact, I have put that to Nick in the past, that the difference between what shall we call the Lorentz theory, because the Lorentz theory uses the Lorentz transformation and a preferred frame, and the Selleri transformations also use a preferred frame. But there's a fundamental difference between them, Ian, because of that space-dependent term in the time transformation of the Lorentz transformation. And therein lies a profound, it is profound. It is what causes all the differences and the problems for special relativity today. And I argue to Nick that I believe Lorentz's version of the theory also suffers from some of these problems, but he doesn't accept that, and that is fine. We could agree to disagree. That's okay.
This is such a key point. Let me just make a quick reply here that in special relativity, to apply his equations, the observers in the non-preferred frames have to synchronize their own clocks. This is also the assumption that Lorentz made for his theory and his transformation equations. However, and to get absolute simultaneity, what Selleri did was, as I said, artificially define a standard frame that all clocks are synchronized by. In doing that, that's how he eliminated the X term in the time transformation. So you can do the same thing in the for the Lorentz transformations. If you apply the Lorentz transformations, but you use absolute simultaneity as defined in the preferred frame, and observers in the non-preferred frame use that same definition for how they synchronize their clocks, then that X term in the time transformations disappears, and it becomes identical to the Selleri transformations. Or what I should say is the Selleri transformations become identical to Lorentz's original transformations, which are well documented and well known, particularly in the dissident community.
But pardon me, Nick, isn't and Stephan, isn't the gamma factor in the Lorentz case? It's in the numerator. Sorry, in the numerator, but in the Selleri case, it's in the denominator. So even if you got rid of that x term in the Lorentz, they wouldn't be the same. Isn't that correct?
No.
Well, Ian, yeah, it's a little more complicated than that, because if you look at the expressions I wrote, the form of the Lorentz time transformation as this is normally written, you are correct. The gamma is in the numerator, but it can be rewritten in a form where it looks like the Selleri time transformation, where it goes in the denominator, that it becomes T over gamma minus Vx prime over C squared.
That's when you substituted for x prime using the equation, and you juggled around. I saw that.
Yes. And then it comes to that, and it allows you to make the better comparison. But very quickly, those points that Nick raises about clock synchronization, again, I disagree with Nick. As far
These are facts.
No, they aren't facts. I am saying that clock synchronization means one thing: clocks telling the same time for the same event. What has happened in the literature, people come up with all kinds of conventions and all kinds of stuff to say they're synchronizing clocks. When you have synchronized clocks, it means one thing and one thing only. The clocks tell the same time for the same event. And I am saying that Selleri's transformations there's no issue with synchronization, where you change synchronization and you get this or you get that. The equations as I have presented them, and in the bottom line, Ian, the equations that I have presented mean that the Selleri transformations represent the real world. You see, at the end, that's the test. The test is, do your transformations make predictions that accord with the real world? And I am saying the Selleri transformations, in the form I have written them and that Selleri has written them, they accord with the real world. The Lorentz transformations, whether in the Einsteinian form or the Lorentzian form, I have pointed out to Nick that the Lorentz transformation, and I showed it this morning, predict constant line speed. That is something Nick refuses to accept, but it is true. The analysis, just a minute, Nick, please. The Lorentz transformations predict constant light speed. The analysis shows it. If you want to escape that, you have to show an error in my analysis. And the analysis is so simple. It would be easy to find if there's an error. And Nick has never shown me an error in that analysis, but goes off on these clock synchronization procedures, which really we don't have to deal with.
Well, if I could just butt in for a second, Nick, if you just permit me. I'm not so innocent. I am aware of the deep differences in some of these interpretations between you two gentlemen, and that's fine with me. That's fine. I might say that the very reason that you're speaking today to us is because you referred to us, to me, through Nick. So I'm delighted. It's worked out very, very well. Thank you very much. I wouldn't have known you had it not been for Nick. So I've no problem with it, with the disagreement. If you want to say a few words,
Nick, let's hear
as I said in my introduction, it was nothing but praise for Stephan's.
Of course, and I thank him.
Right. But I think on this point about the X term in the time transformation is a key point, and we have some differences on that, but it doesn't really affect much of what he presented today, because this is a different topic. This is about the STs and the original Lorentz transformations. But what he said about the special relativity special relativity LTs is quite correct. Great analysis, very good analysis on that.
Okay. Thank you very much, Nick, for raising those points. And if I can leave it there for the moment, and just maybe make one or two comments, because it's sometimes of concern that to outsiders, and we're actually looking for people to give us some contrary talks, maybe defending the Einsteinian ideas of LTs and so on. We haven't received any yet, but we're happy to have those talks. And it is suggested that many of us, in the dissident community, we're giving quite contrary views, and therefore the people in the mainstream can dismiss us a bit more quickly, because they say,
Yes.
well, there's no consistency there.
That's correct.
I mean, for my own part, I conceive of the LTs as really just a bit of an adjustment tool, just a bit of a mix-up, because one hasn't adopted the proper full derivatives in looking at this sort of a really question of fluid dynamics. So you have to bring in these quick fixes, the gamma factor, which is really a quick fix. However, if you just put in the ordinary partial derivative without putting in the full derivative, well, then you have to use something like the Lorentz transformations in endeavoring to make the Maxwell equations or the wave equation invariant. And that's perhaps how the Lorentz transformations were adopted in the first place. Now, I'm just wondering, these Selleri transformers, which seem to accord with experiment, as Stephan has been showing us, how were they dreamt up in the first place? Was it just Selleri sitting back in his bath one day and thinking, these would work very well mathematically?
Not at all. Well, I can't say how he thought about them, but his work shows that he took those two experimental facts. Although Nick says the two-way light speed is not constant, the information that I have is that it is, and Selleri used that and what we call time dilation of decaying particles, and it is those two experimental facts, Ian, that he used and set about. So he wrote down, and if you look in the textbooks, you see how they derive the Lorentz transformation. They write down these general linear equations with many factors, and then gradually work out the values for each. Some go to 0 and so on. But he did the same thing, but he used those two experimental facts instead. And that led him to a set of transformations where there was one parameter, he calls it E1, where in fact those equations, and I call them the universal set, if depending on the value of E1, you could get Selleri transformations when E1 is 0, or you could get the Lorentz transformations when E1 takes on a different value. But to answer your question specifically, it is a systematic and methodological approach that he used to come up with those equations. He followed the scientific method, Ian, where he started with an observation, those two experimental facts. He then codified it, came up with his model, his transformations, and then he tested the predictions of those transformations, which is what I have been continuing to do. Okay. So that's what happened.
I have noticed, incidentally, one or two other names, maybe they were working along similar lines. One was Edwards, I think, and the other was some other Italian person, maybe with a long name beginning with T. You don't, that doesn't ring a bell.
Yes, I think I know. Edwards, if it's the Edwards I am thinking of, he tried to derive the Lorentz transformations without using light speed constancy. He tried to derive it using two-way light speed instead of one-way light speed constancy, because I suspect, Ian, he realized that light speed was not constant. So he had to come up with something in an attempt to save special relativity. But then I pointed out in one of my papers, even though you may use something else to derive the Lorentz transformations, the fact is the Lorentz transformations predict constant light speed. So you still run into problems. You can't escape. And the other chap, I think it's Tangelini is his name.
Could be. Yeah,
yes.
Could be.
He wrote down the Selleri transformations way back in the 60s. He published it in a paper where you could say, just he speculated as according to his paper, wrote it down, and then said to get them, you had to do some special kind of clock synchronization. And then he immediately in his paper discarded it. So even though some contemporary writers attribute those transformations to him. I don't.
Okay.
Because he discarded them. Selleri is the one who provided a sound foundation for those transformations going forward.
Okay.
And that's
This
why
was like about 40 years ago or something, was it? And he's deceased now, Selleri.
Yes, he is. He is deceased. Yes, yeah. Okay. So, Ian, we wanted to hear Eric and James.
Yeah, exactly. You've just I'm just waiting to be able to have two people in the green room. Eric is first. Now, Eric has made some very radical suggestion that what you've said, as far as I can see from what he wrote, would indicate some contradiction with quantum mechanics. The very, very long subject. So I'd ask you, we're running out of time. I'd ask you, Eric, to make that point as briefly as you can, please.
Yeah. Well, look, it's really great, Stephen. It backs up my work, and congratulations. I've always been worried about this term in the Lorentz transformation, and I published 10 years ago in Progress in Physics that this was wrong. And it relates to the derivation of the de Broglie equation in the way he used it to get his famous wavelength equation. He used the Lorentz transformation and derived this horrible equation where the speed of light squared equals a phase velocity and a group velocity, and it or a particle velocity. Also, that's actually the particle velocity. But so if you make the particle stationary, it means that the phase velocity is infinite. And so that's why they say that the wave is a probability wave, that it's not a real thing. So it leads to all this entanglement and weirdness and ghost waves. So it goes all the way back to de Broglie's derivation. And so you fixed it. I'm real happy that we got rid of this term, that we don't need it. It fixes quantum mechanics. So, but I predicted it way back in my paper.
What year was that, Eric? What paper?
Yeah. The 2014 Progress in Physics.
So sometimes things come together without our knowing it all the time.
Good. I'll go look for it.
Yes. Yeah.
So I think Stephan will probably look at that in more detail and maybe come back to you about that. It's an interesting. I shouldn't really call it a byproduct. It's a fundamental aspect of this. If it's as you say, Eric.
It's closely related. You fix the Lorentz transformation, then you end up fixing quantum mechanics, because this is one of the ground floor derivations. The most important equation, one of the most important equations, is a de Broglie wavelength equation, and it makes them interpret the wavelength as this probability thing that has no real substance. Because
so what's the term in the Lorentz transformation? We can't really see that. Is that the x? Term. Is that the x dependence from the t equation?
Yeah, he got rid of the Vx over c squared term.
Okay, thank you.
That's great. That's great. It removes this horrible other equation that they say has infinite velocity. And so you don't have that anymore.
Okay. I think we see what you're saying. Yeah. Thank you very much.
So it ends up.
Okay.
The ghosts go away from quantum mechanics. All right, I'll go. Thank you.
That's remarkable byproduct. Yeah. Thank you very much, Eric. Indeed. Yeah. Thank you indeed. Now, James Keane had a couple of questions, which I'll let you put yourself to them. They're related to practical applications of the STs and so on. And
very good question. Very good.
A new version of SRT?
Yes, and in fact,
would you like to express this?
Congratulations on the achievements. Congratulations on the achievements in your career and in the work you presented today, sir. I just got two questions that you might want to answer sort of on a level, perhaps, for those of us who don't necessarily eat, drink, and sleep with special relativity theory every day.
Okay.
The first of the two questions is, what new practical applications, procedures, or devices, whatever, follow from use of STs?
Okay. That's a very good question, and you actually heard Eric alluding to a possibility there. And in fact, in some notes that I wrote up, I indicated that I have tested the STs all across special relativity. The next domain of testing is in quantum mechanics, but I'm not a quantum, I don't know quantum mechanics to that level, so I had to leave it alone, at least for now. But to answer your question directly, James, I would say a couple of things. There's something called, well, the idea that light speed is constant, they talk about it as being Lorentz invariance. Good? And then they go on to introduce something called Lorentz covariance, where these laws keep the same form as you take them through a Lorentz transformation. If, however, the Lorentz transformations are invalid, then Lorentz covariance collapses. It's not a required law of nature. And here is what that has led to. Once I drop that requirement, I have been able to produce a quantum theory of magnetism. Now, there's no real proper quantum theory of magnetism. In fact, how the world sees it is that magnetism is part of quantum electrodynamics. But I have developed a theory, not extensively because it's very complicated, but at least for me, I have generated some results which have allowed me, for example, to better explain superconductivity. And to put it in practical terms, in superconductivity, there's something called Cooper pairs, where two electrons, when the temperature goes low enough, come together. And as a result of them coming together, you have zero electrical resistance and you have superconductivity. Well, the force that brings the electron, and they know the Cooper pairs exist, but the force that keeps them together is, they say it's a rather involved explanation. They call it, I forget the name that they use, but it's really not a convincing explanation. My explanation is that each electron is a little magnet. We all know that. Electrons have intrinsic magnetism. And when they come together, once they are anti-spin aligned, like two magnets, when you turn two magnets around north and south poles, they will attract. And my claim is that that is the explanation for superconductivity. So I have to develop that over time, but that is one of the things that has been generated as a result of generating these results with Selleri transformation. Another quick result is there is the Lorentz force law, which has a certain form when you go to the moving frame. Well, Selleri's transformations predict a slightly different force law, which there's a new result there, and I have used it to explain a phenomenon where electrons moving in a circuit actually cause a charge to appear on the surface of that circuit. There's no explanation for it in conventional electromagnetism. And I think this new force law provides a possible explanation. But this is all areas for further research, Jim. But I'm excited about it all because I think we are actually onto something. And here is an opportunity. I put it to this group that what we have been searching for all these years, which is something to replace special relativity, is actually available. And I'm putting that to this group as for their consideration.
Well, that gets to my second question. In terms of what the take-home message we might have from your presentation today, on the theoretical level, are STs, you're essentially a new version of special relativity theory.
Well, there are some.
What's our take-home message there?
The take-home message is the Lorentz transformations are wrong, and the Selleri transformations are the correct replacement. That is the message I want you to have.
And therefore, SRT is wrong.
Yes, absolutely. All of special relativity is wrong. Oh yes. Thank you, Ian. Without a doubt. And
so Ian throws in the punchline.
Yes, he did. There are similarities, mind you. The Lorentz transformation and the Selleri transformations have the same space transformation equation, but they have a different time transformation equation, as you have been hearing. So yes, the take-home message is I am offering you the Selleri transformations as the correct representation of the real world, and that indeed special relativity based on the Lorentz transformation collapses.
Well, I hope we can hear more from you. Thank you, Ian. I'll sign off now.
Thanks very much for your comments.
Thank you, Jim. Thank you for your comments.
So that's an important point, because we can argue until the cows come home as to whether Einstein was using a different version of what Lorentz ether theory had encompassed and so on. But, once one falls, the other falls, because he's using the same equations in the 1905 paper. Yes. I just maybe had one point before we're obviously running out of time. We have to wrap up very shortly, but just one point, because a lot of comments coming in, Stephan, with regard to ether and the medium for transmission of waves and so on. What's your view, or through the Selleri analysis of the ether, of the existence or otherwise of an ether?
Yes, that's another very interesting question. I happen to believe in some kind of medium. The ECI frame is really a frame like an ether. It is really like a local ether, because the light in there is constant at C. And remember, electromagnetic radiation, light waves, they are a function of the permittivity and permeability of space, which is this medium, is something there. You measure this, you measure permittivity, you measure permeability, and C is, 1 over the square root of the product of those terms. So therefore, there is something there. And I believe, certainly at the local level, mean around Earth, the ECI frame corresponds to the local ether. So I support, that's my view, and that space isn't empty and there's no ether unless, no, I don't believe that at all. It doesn't accord with the many results that we have, especially what I have now presented here today.
And you mentioned the preference of using first order in V over C experiments and rather than second order and so on. But do you have any view with regard to the concept that what we've seen, insofar as we've seen from many of these experiments, is that if this field, whatever we call it, an ether, or call it the ECI field, that is effectively carried by the Earth in its revolution around the sun, but the Earth would actually spin through it in its daily rotation. Do you accept that as well?
Yes, I support that. We know that the ECI frame, it moves with the Earth in its orbit around the sun, but it doesn't share the Earth's rotation. So the Earth is rotating past this thing that is traveling with it. Hence, all the results that we have gotten, the C plus and minus VEN, that's directly as a result of simple explanation, is that it's spinning within this ether that is moving with it. I mean, it is all very, very consistent, throughout.
Yeah. I don't know if we have time for one more, but I just say the last one. I don't know if it's possible to answer it so quickly, but
I will. Yes.
I tried to put it up here. It's Harry just saying, no, sorry, the wrong one. Well, they're all important, but my cursor's gone a bit haywire here. Here we are. If the Selleri time transform is correct, then what is the mechanism that produces that result physically?
Good. That's a very good question. I haven't at the moment concerned myself with the causative factors, Ian. I focused on getting the correct transformations. In fact, in my discussion with the group, I have often pointed that out because I've been asked that question. I really do not have an answer. I have some tentative things that I'm thinking about that I've seen, but I have not addressed that question. So the answer is, I don't know.
Okay. Well, that's a very direct and honest thing. I mean, for my own part, I feel that many of us, I could start mentioning names, even speaking for others, which I ought not to do. People like Nick and you and Harry and me and Franklin and so on. You know, we're all delving in an area, and there's actually a broad agreement between us. We have our own different ideas with regard to the details, and in some cases we don't know. So I think, as distinct from maybe one or two of the people here whom I'm still trying to get to speak to us someday, who are just saying that we're off our rocker because the textbooks say that LTs are the correct one and so on. We shouldn't be questioning it. But the few people I've mentioned there, you know, and I think Jim is very sympathetic to that view as well. You know, are really, we're not barking up different trees actually. So the time really has come now where we have to wrap up. But I'd like to give you a minute or two, if you wish, Stephan, just to say a few words in conclusion before I officially close the meeting. So I'll just put myself away from the screen and give it all to you for a brief summary.
Yes, thank you very much, Ian. And I want to thank all the participants for the comments that you have made. That has enriched the whole experience for me. I have been working on this, as have many of you, for a very long time. And over the last year, I have put together, through this group that I work with, Nick and Harry and all of them, I have been testing my results. And I am at the stage now where I feel quite confident that both that this special relativity is wrong because the Lorentz transformations are incorrect, and that it is easy to show that they are incorrect using the GPS clocks, and that the Selleri transformations are the correct replacement, so that no longer does the dissident community have to be scurrying around looking hither and thither. I am putting on the table a result that incidentally has been published in the mainstream literature. This is not a result that you would say published in a dissident journal. These are mainstream results that I have examined, and I'm confident that these results are correct, and I put them to all of you. And I thank you, Ian, for giving me the opportunity to speak on this matter this morning. I hope I have influenced some minds at least to look at my paper, which is at ResearchGate, and I hope to do another presentations of some more flaws in Lorentz transformations in the future. Thank you very much, and my best wishes to all.
Well, thank you, Stephan. I think we owe you a great debt of gratitude for the trouble you've gone to give us this talk, and your papers. I mean, I certainly have been influence, or I've been made very enthusiastic by reading your paper. The first time I said, "Oh, what's he talking about?" And then it prompted me to go in very much more detail, and it became quite clear what you were saying. And I agree with a lot of it. I do have my own particular ideas, you know, and I still harbor a doubt that perhaps the Galilean transformation, you know, in the right context would be sufficient. But I think you've made this case very cogently. And you've gone to a lot of trouble. And as I say, quite a number of us in the dissident community, I think, are very close to you. It would be easier to enumerate the similarities rather than the differences. And I omitted to mention Dennis Allen, who actually I think I could include in that group. Unfortunately, Denny hasn't been participating recently because he's not well at present. But I hope he'll come back in the near future. It devolves upon me. I'm always delighted to have a speaker who is so able and competent and deals so well with the questions and in such a good humor. It's always nice to have gentlemen from in more salubrious climes than at present. Well, we've had terrible weather, which just really dissipated last night. Actually, we have sub-zero temperatures, but I know you don't have to put up with that. But I think you've given us a lot of food for thought, and we'll perhaps come back to this. In fact, I'm even so bold as to repeat what I said earlier, that some of these other tests in the relativistic domain, which perhaps I interpreted I misinterpret some of your tests as being in support of LT rather than against them, but you may come back and give us a further talk on some of those. You've certainly given me much food for thought with regard to the Selleri transforms, which I hadn't really been familiar with at all. I've been looking at the Lorentz transformations, and this is something that we can deal with in much more detail. And actually, the comments that have been coming in on the social media, I thank you all for making those comments. I know we haven't dealt with many of them, but it just indicates that we have a lot more to deal with in our conversations over the coming months and perhaps hopefully years. And thank you very much for everybody in the green room as well. Sorry Harry couldn't come in, but we had Franklin helping today. He had been away. And Nick's points, of course, were really valuable. Thank you, Nick. It was very important to have you here today because you are an expert in this area. And Eric made this almost unbelievable point, but he gave some reasons for it, that this reduction of the time to not having a spatial coordinate was dealing with these views. So I think Nick might want to come back quickly. He's making a lot of... so, are you just saying goodbye, or did you want to say something, Nick?
Yeah, I'd like to say something. Basically, the Selleri transformations reduced to or equivalent with the Lorentz original LTs. And this thing about the X term in the time equation is a red herring. For example, had Lorentz said, okay, we're going to use synchronized clocks in the preferred frame, that would go away. So the question isn't the X term in the time equation, it's understanding the physics that was there, because Lorentz has one physical model. In that physical model, there is no X term. There's just one physical reality. You don't transform it into another physical reality. So that if Eric Reiter had read Lorentz, he would have come to the same conclusion that he did about the STs. So if you understand the physics behind the math, then you will see that these two are equivalent, and you'll come to the same conclusions in quantum mechanics or whatever. So I just think that's a very strong point, and one should not dismiss the Lorentz transformations as, both of them at once. They're qualitatively different, and if you understand the physics rather than just look at the superficial math, you'll see that all the points you can make for the STs, you can make for the that are positive, you can make for the LTs. And Selleri started with relativity and began to incrementally improve it. So there's a lot of history and papers and writings on the Selleri transformations and their predecessors, the ITs, the inertial transformations.
Yes.
That have relativistic trappings, which is not a positive in my view. So I think, there's already a strong group that thinks that the Lorentz theory, with or without an ether, just, there's a preferred frame, is the way to go. And to say that, no, that isn't the right way to go, we need to go with the Selleri, just sort of splits the dissident community. I think we take all of what Stephan had said and just apply it, and instead of introducing a new name and new terminology, just say, okay, here's a nice deep look into what the Lorentz's original transformations will do as a valid alternative to special relativity. Thank you.
Okay, well, thank you very much. Unfortunately, I think Stephan has left, but he will be aware that these are available immediately, actually, after the meeting as recordings on YouTube. So he'll be able to listen to those few last comments. And indeed, my very last comment, I've made penultimate comments and anti-penultimate comments. My last comment is to thank Stephan very much for taking the trouble of giving us this talk early morning in Trinidad and Tobago. And I think it'll give us food for thought. And I'm looking forward to further comments on what he said today. So I'm going to end the lecture now. Please keep a note on the coming sessions. There may be a session by Roger next time, and I'll be back again, hopefully, with another invited talk. So without further ado, on behalf of CNPS, I wish you all a very, very good day, and thank you for your attention and attending.